Assalamualaikum warahmatullahi wabarakatuh, and hi, my name is Arifa Irdina from Group 6, and we will be presenting the integrated design project for methanol production. First and foremost, I will introduce you to our group members, which are Adam, Singyi, Jiamin, me, Arifa, and Afi. So, methanol is one of the most widely used building blocks in the chemical industry, serving as a key feedstock for fuels, plastics, and countless chemical processes. For this project, we selected the conventional syngas based route, which is a pathway that has reached Technology Readiness Level 9, TRL9, meaning it is fully mature and commercially proven at scale. This makes it a reliable and well understood foundation for our design. And beyond conventional production, this route also opens the door to blue methanol, where carbon capture technologies can be integrated to significantly reduce the process's carbon footprint, adding a meaningful sustainability dimension to an already established pathway. And at the heart of our process design is the combination of a multi-tubular packed bed reactor, PBR, with a twin bed pressure swing adsorption system, PSA, enabling efficient methanol synthesis and effective gas separation and recycling. Our three main objectives are firstly to identify the kinetics and operating conditions, second is to design the suitable reactor and purification system, and lastly is to achieve 99.5% pure methanol. The next part will be presented by Jamin and Singyi on the reactor system.
Hi, my name is Ko Jamin. So I'll be presenting about our reactor system. First, we need to understand the reaction kinetic since it allows us to predict conversion and selectivity under industrial conditions. Since we choose the conventional syngas route for the methanol production, here are some chemical equations we involve. The first one will be the primary reaction, which utilizes the carbon dioxide to produce methanol. There are also some side reactions, which are secondary methanol synthesis through carbon monoxide and also the reverse water gas shift. So, to calculate the rate of reaction, we can use the formula provided and we focus on the primary synthesis, where the R is the rate of reaction, K is the rate constant, and C is the concentration of each of the component. So, to calculate the K value, we can use the Arrhenius equation.
I'm Singi and I'll be talking about the process model. First of all, the synthesis of syngas will be done through the mixing of methane and water stream, S1 and S2. Then, a conversion reactor is used to undergo steam methane reforming and water gas shift reaction. Then it's passed through a cooler and sent into a separator to separate out the excessive water. The resulting stream S7 is then sent through a heater and a compressor to reach a temperature of 250 degrees Celsius and 8000 kilopascal. This is the optimal condition for the methanol synthesis to be undergo. Then the S9 is mixed with S12, the recycle stream, and then sent into the packed bed reactor. In the packed bed reactor, we have three reactions, which is CO2 hydrogenation, CO hydrogenation, and reverse water gas shift reaction. Then S11 is passed through a splitter to create out a stream to be recycled and also a stream sent into the component splitter. The component splitter helps to split out the impurities of the product stream. And S20 is then sent through an adsorber to reach a final methanol product with 99.5% of purity. To add on, the recycle stream is done to increase the feed input to the PBR. For the reactor design, we chose to use multi-tubular fixed bed PBR with copper, zinc oxide, aluminum oxide catalyst. The tubes are surrounded by boiling water jacket for heat removal, and it will generate high pressure steam as a useful byproduct. Moving on to the energy integration, methanol synthesis is an exothermic reaction which will provide heat. The steam produced from the PBR will be recycled upstream for reforming process. Thus, it reduces the external energy demand and improves the efficiency of the whole process. The conventional syngas route is chosen because of its high level of technology maturity, currently sitting at TRL9. Based on the current global infrastructure of coal and natural gas, it provides a steady supply chain of syngas, thus act as a reliable feedstock supply. This conventional approach produces a consistent production file and is suitable for large-scale industry.
Now let us continue with operating condition. From the first graph, we can see as the temperature increases, the CO2 conversion will also increase. This is because for the increasing temperature, the reactor can gain more kinetic energy to overcome the activation energy, hence more conversion. Second graph, we can see that as the pressure increases, the CO2 conversion will also improve. This is because increasing the pressure will also enhance the concentration of the reactants, so more conversion. However, moving to the third graph, we can see that as the feed rate increases, the CO2 conversion will reduce. This is because if lower feed rate, the reactant can stay longer in the catalyst bed and have more interaction with the catalyst. Hence, the production rate will increases. Moving on to the last graph, we can see that as the residence time increase, the production rate will also reduce. This is because the feed rate will reduces along the process. Hence, longer residence time, the lower the feed rate. Hence, the lower the production. So, we can have a small summary, which is the optimum temperature and pressure for the reaction will be 250 degrees Celsius and 8,000 kilopascal. And the feed rate will be 110.19 kilomole per hour. The residence time is 2.27 times 10 to the power of negative 6 hours. By using this parameter, we can get the selectivity of greater than 99%. Last, let us talk about the production capacity. From the symmetry simulation, we get the methanol output to be 9,451.43 kg per hour. However, in real life, we will get the annual capacity of methanol production to be approximately 74.9 million kg per year. After calculating and comparing, we will see that the annual capacity in real life will be lower than the simulation. This is because in real life, we will get the lower yield because of the catalyst deactivation and heat gradient.
Moving on to the reactor effluent, it is critical to note that our output isn't just a pure methanol. As shown in the composition table, the effluent contains a mixture of the desired product alongside several impurities that must be managed. Composition overview. The primary species present include the hydrogen, carbon dioxide, methane, and also the water, with the concentrations ranging from approximately 0.05 to nearly 1 mol dm cubic. While methanol is our goal, these secondary components significantly impact our downstream processes. We categorize the impact of these impurities into three main areas. The first is the catalyst protection. Water is a major concern as it reduces methanol purity and, more importantly, act as a poison to the downstream catalyst. Second, product grading. To achieve industrial-grade methanol, we must efficiently remove carbon dioxide and carbon monoxide as they directly lower the final product quality. And the last, purity dilution. While hydrogen and methane are chemically inert in the final product, they are still reduce our overall purity percentage and must be separated for recycling or disposal. Understanding this specific concentration profile is the first step in designing an effective separation and purification sequence. To address the impurities identified in our effluent, we have developed a robust three-stage purification strategy. This system is designed to maximize methanol recovery while ensuring the final product meets stringent industrial standards. The first stage will be the initial separation. The process begins in the separation column. The first stage utilizes gravity separation at high pressure and approximately 49 degrees Celsius. By exploiting density differences, we are able to remove the bulk of the liquid water, protecting our downstream equipment from heavy moisture loading. The second stage is the precision adsorption. The stream enters the adsorption column. Here we utilize the zeolite 3A, a highly selective adsorbent that captures remaining water. Because zeolite 3A has a specific pore size, it allows methanol molecules to pass through while trapping smaller impurity molecules and effectively boosting the purity to the industrial grade. The last stage will be the continuous operation and regeneration. To ensure the plant operates 24/7 without interruption, we utilize a twin bed pressure swing adsorption (PSA) system. While one column is actively adsorbing impurities at high pressure, which ranging from 3 to 10 bar, the other is undergoing regeneration at a lower pressure or vacuum, which is approximately 1 bar. These rapid cycles prevent thermal degradation of the adsorbent and maintain high efficiency over long term. By combining bulk gravity separation with high precision PSA, we achieve a reliable, energy efficient route to high purity methanol production.
I'll be moving on with the adsorbent selection. So for the purification stage, we selected zeolite 3A as the adsorbent. Zeolites are crystalline microporous material with very high surface area and uniform pore size, which make them excellent for separating molecules based on polarity and size. In our system, the strong cation sites within the zeolite framework, such as sodium and calcium, interact strongly with polar molecules, like water and carbon dioxide. This allows methanol to pass through while impurities are selectively captured. To model this adsorption behavior, we compared two isotherm models, Langmuir and Freundlich. The Langmuir model assumes a uniform surface and monolayer adsorption, but this does not reflect the complexity of the zeolite surfaces. And for the Freundlich isotherm, on the other hand, accounts for heterogeneous surfaces and multi-layer adsorption. Our data showed that the Freundlich model gave a better fit with a correlation coefficient close to 0.99 or the R. This confirms that multi-layer adsorption is the dominant mechanism in our system, making the Freundlich model the most suitable design for our design purposes. For our column design, the adsorption system is designed as a twin column pressure swing adsorption unit or a PSA. This means we have two beds operating alternately. While one column is online capturing the impurities, the other is offline undergoing through the regeneration process. This arrangement ensures the continuous purification without downtime. The columns are operated under countercurrent flow, which maximizes contact between the gas stream and the adsorbent particles. This prevents channeling and ensures uniform adsorption throughout the bed. In terms of operating conditions, adsorption typically occurs between 3 and 10 bar, while regeneration is carried out under vacuum or at near atmospheric pressure. The temperature is maintained close to ambient, around 20 to 40 degrees Celsius, to avoid thermal degradation of the adsorbent itself. Overall, this twin column PSA design provides a reliable and energy efficient purification system capable of consistently achieving the target purity of 99.5% methanol.
Lastly, for our regeneration strategy, we are using pressure swing adsorption system, where desorption occurs by reducing pressure at constant temperature, followed by purging with a small fraction of product stream. And this PSA system avoids high temperature so that we can prevent the degradation of adsorbent. And it is also faster than TSA, which usually takes about a few hours or so. There are a few advantages of PSA, which are continuous operation with alternating columns, lower energy demand than distillation or TSA, and also maintains adsorbent performance over multiple cycles. The pressure swing adsorption system offers notable sustainability benefits by reducing the overall thermal load. It lowers the external energy input required to run the process. And additionally, the system supports long-term operation with minimal adsorbent replacement, cutting down on material waste and maintenance demands over time. So, to conclude, the idea of integrating a multi-tubular packed reactor and twin column PSA system provides a feasible solution for methanol production. This is because it achieves the industrial purity standards of 99.5%, all the while consuming energy efficiently through heat integration and adsorption based purification. And this integrated system ensures reliability and scalability by employing the mature syngas route, which offers a pathway toward blue methanol, and it is very beneficial for sustainability in the future. So that is all from our group, Group 6. Thank you very much.